for the live stream. So it should, okay. So we are live, welcome. Welcome to another wonderful talk within the frame of our module, Emerging Fields in Architecture. Today we have Guy Trotti here as a guest. He's an architect and industrial designer. He taught space architecture for many, many years, first in the College of Architecture at the University of Houston and industrial design at the Rhode Island School of Design. He was one of the co-founders of SICSA, the Sasakawa International Center for Space Architecture. It's still the only university that offers a master course in space architecture. And presently, he is also teaching, and he has co-founded a space architecture program at the Arizona State University. Also interesting about Guy is what we discussed shortly before, but maybe we hear also a little bit in his lecture. He is an explorer, means he has not only had interesting projects in Earth architecture, but also space architecture, but he also circumnavigated the Earth in his sailboat. So I'm happy to have you here, Guy. It was great that you take your time. Welcome, and we're looking forward to your talk.
Well,
the floor is yours.
Thank you, Sandra, for the kind invitation to participate with your students, and thank you to the students to be present today. And I will tell you a little bit more about how I got into this field, since you're exploring different fields in architecture, and how this whole design aspect of participating in the space program started. There were things. My personal journey was coming from a field of architecture. Like fourth generation architects in my family, so I grew up in an architectural studio, and when I arrived to the United States, it was right before 1969. I came here to school, to undergraduate, and landed in Houston, just a few miles from the Johnson Space Center where astronauts live and train, and got immediately fascinated by photographs like the ones that you see now on the screen, of astronauts and hardware and the most absolutely beautiful details. I always call space architecture like designing jewelry, because it's so detailed, and every element is just gorgeous, titanium and special materials and so on. So I will speak a little bit about that, and then kind of a trajectory of my work on the space station, the lunar structures, Antarctic, and then we can open it, and spacesuits, and then we can open it for discussion. So, the story of humans wanting to go to space, or looking at the moon and the sun, they were always kind of the dream of walking or being in these planets. Obviously goes back to when we lived in caves, that we dreamt of these, had these dreams and kind of this vision that every day you lived by the influences of the moon and the sun and the planetary movement. So, and then also in the arts, it was always reflected, this idea of going to the moon. This painting, the one on the left, I think all of you have probably seen this picture, is the first picture of the Earth taken from Apollo 8, when the Earthrise, and really kind of changed the perspective. You all have lived in an era where we have already been in space, but this was the first time truly when we saw the Earth from far away, and see it as the blue sphere that it is. Then on the right is George O'Keeffe, an American artist. She paints the ladder, the ladder to the moon, and it's always kind of, to me, an iconic photograph of our dreams of conquering space and really moving away from our planet Earth. So in my career, I worked heavily on the space station. I spent more than 20 years from before the inception of the space station, where I worked on the early concepts before the ISS was called that NASA was intending to go to low Earth orbit. And then to do that, I spent a lot of time on, you can see here on the right, on the what we called the vomit comet. At the time, this KC-135 cargo plane, it was empty inside, as you see, and we tested many of our designs in this plane. So this is the way we simulated zero gravity to try to prove our concepts of how things might work in zero gravity. So it was that, and then a lot of time, again, underwater diving, which is the other place to simulate. And then I worked as an undergraduate. I did lunar base as a project, my thesis project, when I was finishing architecture. It's the picture that you see here on the left, bottom left. And that was really a research on different ways to build on the moon, how different structural systems, materials, and logistics, and how people would live on the moon. That ended up at the Air and Space Museum and the Smithsonian here at the National Museum of the United States, and launched me into a career. When I finished that, it was in '74. And then I did a master's degree for 2 years working on space station design, because the space station was coming up, was the end of the Skylab space station that I'll show you a photograph of, so you remember it. And and that just absolutely changed my whole life in terms of architecture. As I said, I was fourth generation architects from the same studio from my great grandfather. I'm originally from Argentina. I was supposed to go back to Argentina and run the business, and I never did. I fell in love with space, and I remained in Houston for another 20 years doing that research. So, it's been an incredible trajectory, experiencing things and exploring so many things that I never dreamt as a young man that I could participate in, particularly coming from, a faraway country like Argentina. So this is, again, more experiments, things, different flights that we worked on the zero gravity plane. So as Sandra mentioned, I'm really interested in adventures, exploring, the planet. I've been in all this different, on every continent on the planet, but one of the most significant things that I did with my partner, Dave Newman, who is an aerospace engineer and actually was the #2 at NASA during the Obama administration. So the two of us alone went around the planet on that red line around the map, discovering not only really new islands and new places that we hadn't been, but actually having interaction with people, cultures, understanding a lot of different types of building systems and building ways that I've applied throughout my career as well after that. We call our lives BC and AC. It's before circumnavigation and after circumnavigation, because it really changed the way we live. And the way we approach our lives on Earth. And so we were named by NASA Solar System Ambassadors, which was a great little badge to carry with us that allowed us to interact with astronauts everywhere we stopped, and we had a three-way video, which it was not like as easy as Zoom today or Skype. It was really difficult, at that time. It was in 2001, 2003 that we did this. And you had to actually go to corporations or universities that had the systems to actually do that. So we had three-way communication between students, mostly high school students and university students, but and locally where we were. And then we would bring in a high school from the United States, from different states, and then astronauts from NASA, usually from Houston. So, and then we took the kids that we were with, sailing with us or teaching them about navigation, and we taught about exploration of the sea and space. So during that time, we spent also a lot of time underwater experimenting, and really approach the whole idea of the trip as a space experiment. Since we're both in space, we really took every element and have many notes on, navigation. What tools should we take? How much material we should take on board in terms of spare parts? How do you use local materials when you arrive somewhere to fix something that broke and there's no other way to go or purchase that piece of equipment? And how do we do repairs? And food, and how do we sleep, in terms of how do we separate the days? Someone is always on duty, make sure that we don't run into another ship and so on. So it was really an amazing exploration. So basically, I will now talk to you about low Earth orbit. So we start nearby, where we first explored space and the space environment. And I'm not sure how much have you researched this area during the semester, so I might be repeating many of the things that you already studied. But as the space environment is quite harsh, in terms of many different ways. We have huge temperature variables between when you're in the sun or on the dark side of the Earth, or again, radiation that is constantly flowing, the galactic radiation flowing through space, where in the space station we are still protected by the magnetic field of the Earth, the Van Allen belts, but you still get affected by radiation, particularly if you have solar flares coming at you from the sun. Then you need to shelter and create the shelters within the space station to protect the crew. And then the most important thing from the architectural point of view and from the design point of view is that you are in zero gravity. The gravity force that we deal with in space and on Earth disappears basically when you are in space, and all of a sudden structures behave totally different, because the other thing is that we're in the vacuum, and the vacuum basically dominates the structures of space, where gravity mostly dominates the structures here on Earth by designing columns and beams, and everything is in compression, and we need a significant amount of mass to build large buildings. Where in space, basically everything is trying to blow up. Every structure becomes inflatable with a rigid or fabric, and then all the structure, the pressure shell is in tension. It's really trying to blow up. So these are significant characteristics that really turned me on when I was a student, because having grown in an architectural studio, designing and studying columns and beams and materials and compression, this whole ability that now we could use 360 degrees of a space, not just the floor and walls, but actually the ceilings, And then us humans become really like a bird. We can fly or we can swim like a fish, and appreciate and be able to touch and interact with every surface of the built environment. So this was really critical for me to use as a new method of design, or a new, not method, but actually a new ways to design, given this massive changes in the characteristics of the environment. To get to space, it's not easy. We use these rockets, right? When I started this, there was only the Apollo rockets, the Saturn V, and so on, and that was that. Basically, the Russians had their assistance, but at the time there was no collaboration. So depending on the Saturn V and Saturn rockets, and it takes a tremendous amount of energy to get to space. We need this launch vehicle that you see here just to get to low Earth orbit and launch that triangular little capsule, conical capsule that you see on top of this massive rocket that is 100% fuel. So it's a massive endeavor to get out of the Earth's gravity, and it takes a huge amount of energy to get there. This is actually a Russian launch from Baikonur. So today is a totally different story. We have private companies designing launch vehicles, small and large, as you see here. I'm not going to go through all of them because I think maybe you have studied them, but this gives you a little bit of the history and the sizing of the vehicles. The one on the left is the Saturn V, the large rocket to go to the moon, and Starship is coming, and we have already launched an SLS. So it's now a lot easier to do that, and I think that is what has opened the commercialization of space, where now we have companies looking at building commercial ventures, both on low Earth orbit and the moon. So this makes it truly an exciting time. I think you are living in a kind of another golden era of space, given that we are there to stay, given all the different ways that we can make it to space. And access is everything. And before, we're limited always or by one vehicle, like the shuttle, for instance, that was a really difficult vehicle to operate. So this was the first space station, Skylab. This was a tank, basically, of the Saturn V that was transformed or designed as a habitat. They added some power modules, this kind of cross design for the solar panels. Were kind of the first solar panels that were coming to, that were being manufactured. These were not even, there was no commercially available solar panels at the time. This is in the early 1970s, between 71 and 73. And then the lateral solar panels that you see, the gray image, and you see this funny umbrella on top of it, or this little diaper on the space station. The reason that happened is the solar panel on the right of this image never came out. It got jammed during launch in the structure, and they were never able to deploy it. And that cost less energy, the production of less energy for the Skylab, and also heating it up, the less shadowing. And this was kind of the first repair, really, in space. When the astronauts went for the first time to Skylab 1, ended up a crew of 3 there for a month, they deployed this basically umbrella or blanket through a small airlock, and actually were able to reduce or bring down the heat in the vehicle, and able to operate it for the 3 missions that it lasted. The first one was 1 month, the second one 2 months, and the third one 3 months, with a crew of 3 each. And learned a tremendous amount of what it is to live in space from this vehicle. That's where I learned a lot of my lessons when I got into the business. This was in 73, and right when I started the last mission of 73, when I started my lunar base thesis. But truly, there's a series of books that I think you can, or articles that you can see from at the NASA website called Lessons Learned from Skylab. And that is basically debriefing of the astronauts, speaking about the good and bad and designs of the space station, what worked, what didn't work, what could be better, and so on. So there's just a tremendous amount of information for me, but it was the only information, architecture, let's say, or design information that was there. Other than, and then obviously Raymond Loy participated, a great designer that started industrial design, and he participated there, had influence in the window of Skylab, putting one large windows with NASA really wanted to put a very tiny window, and he really fought for this window that was probably about, I'm not sure, maybe 60 centimeters in diameter or so, and did some work in the galley as well for Skylab. And then obviously there was some articles, but not easy, from Russia, from the studies that were being done there in the interiors of their space station. And so that launched me into working on the space station. That eventually was called the International Space Station. This station is about 100 meters long, and houses usually about 6 astronauts to 9 or 12, depending when crews are changing. And as we know right now, we have the astronauts that in a way got stranded at the space station when the Artemis capsule was not functioning the way it's supposed to, and for safety reasons, they stayed on the space station while the capsule returned, and now they will be, I believe, will be returning in February. So that's an adventure that is going on right now at the space station. But it really shows how we are able to work and live in space. And this space station has been on since 2000, actually. Or a little after, permanently habitated for more than a couple of decades. And and it's just truly an extraordinary laboratory to work in. And it was really great to be able to participate in many of the aspects of the space station as it started working on, like my thesis was, what would it be, what would the configuration of the space station would be. And my thesis was based on different ways to assemble space station in low Earth orbit from the shuttle bay. The shuttle wasn't even designed yet. It was conceptually designed, but it was not operating when I was in school. And so we were envisioning in what ways, how do we build this massive space station from the small cargo bay of the shuttle? How do we put 400 and some tons in space from the shuttle bay? And one of the studies, the end of the thesis was whether we use nodes or not nodes. Nodes is this element here on the right that has the different docking modules and different axes. So the space station could grow vertically, horizontally, and also change scales of the modules, which gave a lot of flexibilities, because at the time there was a discussion whether the modules would hook up one next to the other, a cylinder after the other, or directly module to module without the nodes in in between them. So this was a major study, and it was very much part of my thesis. Obviously, there's nothing out there, so we need to supply these vehicles with big humans like you see on the left side, and I think we studied those when SpaceX is doing that. And again, the Russians have their Soyuz capsules that that support it, and then NASA has supply vehicles that are unmanned, and again, several private companies in Japan that also sends material to the space station. So it's really fascinating to think about that it has been over 20 years living in low Earth orbit and doing experiments and building this massive structure there and learning so much from there. I will show the cupola because I think the cupola is really where everybody likes to hang out. This is a place not only for work, obviously, for loading and unloading cargo, operating the manipulator arm from the space station is looking down to the Earth. It's located down below here in this photograph. So that's where astronauts go and really observe the Earth go by. And every time that they have free time, I think everybody migrates to the cupola to take photographs and videos of the Earth and just really get a real sense of where they are from the daily activities on space. Here you see the first inflatable module, which is something that I promoted from day one, this idea of having inflatable structures in space, having the ability to fold them and be quite small in the way they are shipped, and then you would have at least double the volume of whatever you ship or you launch. You can expand them and use them, and this has been performing really, really well on the space station. I think has been there for several years, and actually Bigelow, the company that built this, has a free flyer, quite a large inflatable structure that has been flying. I don't know, probably it must. I don't know exactly the date, but at least 15 years or so, and it's still performing. It has sensors in it, and still working very well. So I'm a big promoter of inflatable structures for space. So this is the interior of the space station. I'm sure all of you have seen it, but if you can imagine it without all the junk flying around, as you see on the floor in this area or the bottom plane here, it was quite clean and quite modernistic, for no better word, when it was launched in the early days of the modules. And then this is like designing this beautiful house, and then you get these bad tenants that leave all the garbage out. So it's like it has grown to having more and more stuff. It's fully packed with things where astronauts have a hard time finding things and so on. But it is really an incredibly working laboratory. So you can see here, the design of a workstation, foot restraints, where you slip your feet on these little platforms to work, and on the workstations, and be able to use, for instance, here a manipulator arm and through video, through cameras outside the capsule. So and how every square inch of every surface is being used, and not just the floor and walls as we do here on Earth. So the orientation here happens because of lighting. You can see the lights are really showing. This is actually a local vertical, as I call it. So illumination is really critical to orient astronauts, because of that's the way we're designed. We're designed to have light coming at us from the top of our heads. That's why we have the eyelashes and eyebrows and our eyelids the way they work is because we basically are designed for sunlight and for light to come from above. And we did some design in terms of color designs and ability to orient the astronauts. NASA did not go that way in all the elements. We suggested some colors that were used, such as the light pinks and the browns and earth tones, but they did. Our concept was that the floor area, the local vertical, and every module should be darker because we are used to having light colors above us and then dark is the floor and the ground and the dirt of the earth. You know, NASA really, in terms of human factors, they could have gone further, but because of budgets and time, many things were left out from a lot of the research that was done for the space station. We spent a good amount of time working on the galley, on the food design and packaging design, and the table design of the galley and the wardrobe for the space station when it was built then. And what is interesting to me about this photograph is that table remains the table, whether we're on Earth or in space. People like to sit down around a table or platform to share a meal, to to be festive and to cook and eat together. These guys here, when crews arrive, there's a kind of a very festive moment, but the food is attached to the table because if not, it would fly away. So we did a lot of studies in terms of how to attach things with wedging or bungees or elastic systems or sticky systems and so on, Velcro and so on. So we did a tremendous amount of work on the galley system for the space station, several years of research, just how to deliver food and food preparation. And again, we experimented with many things that were not applied. We did not NASA didn't get done. So now we're able to grow veggies in space. There's a small greenhouse where experiments are going on in terms of growing plants. If not for the space station, because the space station gets some really good supplies and regular supplies from Earth, but mostly about what we will need and how we would do this on the moon. And there's a tremendous amount of research going on and in growing plants and possible animals in space. In terms of orientation, I always think about in Skylab in the early space station, they send little fish, in a bag of water, and when the fish were floating around in zero gravity and in free space, they didn't know what way was up, just like us, and they were swimming in circles all around each other. They couldn't follow each other. They couldn't orient themselves because of the lack of gravity and the way that light was kind of 360 degrees. They didn't know which way was up. So the astronauts actually hung the bag on a wall of Skylab, and they put a dark piece of paper behind it. And the fish immediately thought, okay, that dark is the bottom of the ocean, and the fish, oriented themselves 90 degrees against and with a, oriented to that bottom, and they all swam happily ever after that. And it was really interesting how simple it is for us to learn and orient ourselves even in environments that we're not used to it. So anyway, so there's a lot of great videos of how astronauts eat in space and how they prepare food, but this is all about the fresh food. This is actually what we dreamt of, and actually build a full-scale galley, within the racks of the space station. So at the time, we have 3.5 racks dedicated for food storage and food preparation. We designed one of the first ovens that were heat injection, which now we call convection, but these were really high-speed heat injection, and microwave. So all these new microwaves that you see today in the market that people use that are both convection and then and microwave, we were just inventing this in the early 80s. And then water dispensers where astronauts can dispense water in different temperatures, whether you wanted cold water for a juice or hot water for soup or room temperature water to drink. So all these were actually designed and installed and trained astronauts how to use them, and we had comments with astronauts. We're always working with astronauts in our studio to come and experiment what we design to give us feedback. And the same thing with the refrigerators and freezers is the left rack here, where again there's no gravity, so there's no convection, so we have to actually inject and push the cold air through the cavity to make sure that you had in every area of the cavity of the refrigerator or freezer, you have the same temperature. So you had to mix the air, forcefully and so on. So, and we spent a lot of time designing different types of tables and restraints, the food containers and so on. But I'm just giving you today a very general idea of how this, how we got into this field and the aspects that we got involved in during the space station. And sleeping was a major one. Astronauts in Skylab were the first ones to sleep on a sleeping bag hanging from a wall, but many of them like to sleep like these folks, just loose. On Skylab being so large, they would go to sleep. These guys are wedged in the capsule, very small, but in Skylab they could sleep in large environments, so they would travel through the night to a different place, and they would wake up on the other side of a very large module or another module altogether, moved by the flow of the air, because the air movement within the capsule is your local gravity, is what moves things out around. And for instance, when people lose something on the space station or Skylab, they always they go to the air return system, the filter, because everything eventually flows to that filter, and you find all kinds of things that you've lost through your day. A couple of days later, somehow it shows up on that area, on that filter. So this is Samantha Cristoforetti. I'm sure many of you know about her. She's an amazing astronaut from Italy, and she is in the crew quarters. The one on the right is the one that we actually proposed for storage and other things, personalized. But and we are really promoted originally to the idea of having soft materials for acoustical reasons. We actually added the idea of having metallic and shine and reflective surfaces like mirrored to make the space larger, to make the field larger. But this is the most private space that you have as an astronaut in the space station. This is the place that you go to sleep, but actually you go and get away from everybody when you have to, or you go there to speak to your family and connect to them in a private way. So, we had light control, airflow control, very much like you have on an airliner or, on an airplane. So we did some conceptual designs as well, or on the sleeping bags, both for comfort and being able to work. This idea of the opening. So if you had a workstation like this in front of you, how to operate, while you are being restrained, and on the wall. So anyway, so we can see how chaotic things can be. So I just really use this slide to remind my design students, when design equipment, to really pay attention to cords and things like that, because as every time you have a cord or springs or cables floating around, they jam, they get tangled, and they're really, really hard to manage in zero gravity. So, so that's kind of the significance of design in a few of the aspects that we encounter when we're designing for zero gravity. But you know, as we speak, we're heading towards the moon. The moon is you know, I dreamt that we would be back on the moon in the 90s. That never happened. That's when I was a student. I thought we would be on the moon by the 90s, but then the way governments are, they didn't fund the projects until now. So, but we are on the way to the moon. We are definitely designing right now a couple of landers to get there. We have the rockets to go there, and that will give us access to the surface of the moon. The idea now is to basically go to the South Pole of the moon. As the moon rotates, the South Pole and the North Pole, there's craters there, as you may know, that never have seen the light of the sun. Therefore, we know that there's some ice. We don't know exactly in what form, but there is water and ice inside these craters. And the idea is to go down to the South Pole and mine them. So the locations all around what is called the Shackleton crater around the South Pole also is where we're planning between, I think, is the U.S. and Europeans and the countries that are part of the space station. I'm not sure about Russia right now, but the idea is to establish or first do research in that area and then maybe establish a small outpost. So the moon environment is a bit different than zero gravity, basically on low Earth orbit, because we have 1/6 the gravity of the Earth on the moon. We have no atmosphere, therefore, and then so there's a tremendous amount of contrast, and it creates difficulty also when you're on the surface to perceive how distance and perspective when you're on the surface, so you don't know how far things are. It's quite disorienting for astronauts. The Apollo astronauts experience that, and also, you know, now the radiation on the surface of the moon is way more damaging, I think, to humans and life, given that we are away from the magnetic protective magnetic field of the Earth. Therefore, we have total exposure. So radiation is a major issue building on the moon, and then extreme temperature differentials from, you know, almost 500 degrees temperature differentials from plus to minus. So, you know, and this is kind of a distribution of minerals and materials on the moon between the dark areas of basalt. Basalt is a local material. There's iron, there's aluminum, there's you know, oxygen in the soil, in the topsoil of the moon, silicon and others. But those are kind of the principal materials. So we need to think, and NASA and everybody that's thinking about going to the moon is thinking about how do we use this local resources, in situ resource utilization, we call it in the NASA lingo. And the idea is to think in terms of architecture, think in terms of habitats. How do we use the terrain and the materials, how we might be able to mine some of these materials, not only the ice for the water, but it's more than water. The idea of going to look for this ice is to then separate it for oxygen and hydrogen, which are the materials combustible materials to use as fuels for rockets. And that the idea is that we could actually mine that, create enough fuel to maybe launch missions to Mars from the moon or from the moon orbit, but make the fuel on the moon. So in terms of architecture, I always go back, and I like to not only mimic nature, but actually mimic ourselves when we started building, we humans started building on Earth, whether it's underground and in caves like in Turkey or here, Mesa Verde, the example of Native Americans that protected themselves from snow and weather and enemies as well with the terrain in these canyons and or in caves. So the idea now is to maybe explore lava tubes that are formed that we know are formed or have been formed on the moon, and going into these caves and through these lava tubes will have incredible advantages because the other thing that happens on the moon is micrometeorites as well as on low Earth orbit. But low Earth orbit, again, we're protected very much by the Earth. So although we do get, the space station gets bombarded by micrometeorites, on the moon as well, we will have, constant bombardment of micrometeorites. So being underground, the temperature is more constant inside these caves, just like as it is here on Earth. The idea is that then we could go into the cave, protect ourselves from the micrometeorites, radiation, temperature differentials, and and basically have this not having to build a shield if it's already built by these caves. So that is an area of exploration that I'm very interested in and doing research right now at Arizona State University on how we might end up building on the moon rather than on the surface, as you see here. This is the lunar base where we explored all kinds of different methods of construction, whether there are those towers in basalt, the inflatable structures of the domes, and then in the background you see using cargo vessels as a laboratory or using them as architecture. So one of the ideas and that I'm pushing on is the idea that not only all the material that comes to the moon gets recycled, so we would have enough energy to melt it back into and then build parts and repairs and structures from the metals that we bring and other materials, but actually use the containers themselves, very much like we do here on Earth with containers. There's container architecture from trucks and train containers where they might be outfitted for quick refurbishing with power lines and ducking for water and gases, so we can use them for laboratories and so on. So the whole idea of then all those containers can be attached to a tower and be part of a building that is in constant motion. You can bring them in and out and use them as remote habitats, as well as maybe fly in orbit, and or melting them and reusing the materials. So anyway, this again, inflatable hangars, which are not pressurized inside, but actually stand by pressure. So for shielding of the sun and temperatures to keep things, protected from temperature and some radiation. And then the building that I just described in the background, again, using a lot of inflatable structures, and then connecting underground through tunneling, because the idea of if we're going to mine, we will have the equipment to mine tunnels and so on, to be able to move from facility to facility, from areas where we might do farming to areas where we would have large spaces for humans to interact, and so on. So one of the elements of construction could be the use of basalt and the regolith, where we might cast them very much like we do here on Earth with casting concrete, but we could cast panels and that serve as radiation protection and assemble them. And then you would have a pressurized environment, whether metallic or inflatable, inside to keep the pressure for the atmospheric pressure needed for humans. And obviously, the idea of the rovers, for rovers, we would need to transport ourselves on the surface of the moon, could dock directly to the habitats or space suits to basically go EVA, extravehicular activity, which means going out and walk around the moon with your spacesuit. So 3D printing is being talked at as a technology that robotically we might be able to pre-build some shielding and some structures before humans get to the moon. So I think all the activities, the human activities will be in high contact and relationship with robotic systems. Are getting smarter and smarter. The robotics are getting much more dexterous and smart given artificial intelligence and programming. So I think we will always have robotic systems as an assistant or a companion for humans in space. And we will be there probably to serve them, to really build, fix them and take care of them rather than and let them do the work. But we would be there to repair, to fix things that would be difficult to do robotically and self-healing with the systems themselves. So with that in mind and talking about rovers, I'm also hoping that initially we not go to the moon and build a big base and find out that maybe we could have built it somewhere else, or really having research enough or find enough about the landscaping for a better location. So I really believe in nomadic architecture, and I did the research on this habitable and exploration, I call it exploration module, but really is a nomadic architecture. And this idea is to have 3 astronauts being able to explore the surface of the moon and use it as habitat, and then the ability to truly understand the surface of a region before you go there. Some elements were used, the shielding, kind of the gold area, are micrometeorite shielding and reflector with solar panels and also radiators to get rid of the heat produced by humans and computers and so on inside the vehicle. It has an inflatable airlock in the back, and then an inflatable structure that deploys at the sides that can connect to another module, and then create quite a significant base for 6 people to live and operate on the moon, and then be able to move to other locations when needed. The idea here is that the rover would work during the sun days, so we have about 14 days of sun on the moon. So during those 14 days, it would be operational, and then it would just come down. The legs, the vehicle goes down on the ground and sits on the ground during the dark period, which is extremely cold and dangerous to move around. Therefore, during that time, then the astronauts would do experiments and work on the vehicle and so on, in the vehicle, and then supplies are on top on the roof for air and water and other expendables. And the idea is that with a manipulator arm, this kind of hook or manipulator arm, is the vehicle can pick up supplies as they come from the Earth and resupply itself. And then and the interior is very simple in the way that these astronauts actually sleep and work in the same place. They have very much like a first-class airliner seat, and so it's tight, but it's comfortable. And then also the idea of having a laminar flow, vertical laminar flow air to control dust if it comes into the vehicle when astronauts go EVA or bring samples, and then the dust will go through a mesh on the floor and actually be vacuumed up and stay out of the air, because we think that the soil of the moon, the regolith, is maybe some humans are allergic. Some of the astronauts, the Apollo astronauts, reported having difficulties breathing or having some sort of allergic reaction to it. And also it has some smell. It seems that it smells like gunpowder and so on. So it's not the best. It's not the best thing to be breathing. We still don't know how these very jagged particles. The particles are very, since there's no wind on the moon, the particles are very jagged, and they they could be harmful to the lungs and so on. So I'm going a little faster here because I think I'm running out of time. Then this shows the purple, the inflatable structure that would deploy from the side when the vehicle is on the ground, and then it will connect to the other one, and then you would have a larger environment to use as a laboratory during the dark days on the moon. So then worked on the biosuit. This is a it's a mechanical counter pressure suit that applies the atmospheric pressure on your body rather than an inflatable suit like we have today. And it's all to create a much more agile suit, so to truly become an exploration suit rather than the big, difficult suit that we use now. So for the moon and Mars, we will need very, very different types of suits. The lines of non-extension, as you see on the bottom, are lines in the body that we have that change shape, but they don't change length. And the idea is that allows for more and more mobility and more flexibility for the suit. So we're in the process of designing the helmet right now, doing some experiments on the helmet right now for heads-up displays and airflow and circulation. And getting away from this massive suit that is so difficult to move. These are astronauts training here in Houston, where they train in the swimming pool and the water, and they operate their missions. But when they do that, they've been hurting themselves, and also worked on ways to protect the astronauts during training, particularly with these pads in critical places where they get hurt. And so we have this inflatable padding that works, that they fix the astronaut inside the suit, inside this vehicle. I call it the smallest piece of architecture built, because you basically live 8 hours inside the suit, and you eat, you go to the bathroom, you drink water, and you work in it. So we did a tremendous amount of work on human protection and astronaut protection systems for the spacesuits. And this is a sample of some of the inflatables that work on the shoulders, and they were having damages in the shoulder and the clavicle system. So I'm all pro of the idea of using the Earth as a simulator. So there's many simulating environments. And I promoted the idea of using the Antarctic as a simulator, because I was very lucky we were lucky to win a national competition here for the design of the South Pole Station, and we won that competition. So I ended up going there with some of my students on my team, and really understand the environment firsthand. So very much a concept that we designed is what's been built. Actually, we won the first and the third prize. This is the third prize. Actually, the concept is the third prize that we came up with, and very similar to what is built today. So anyway, I think it's a great analog, and many lessons learned from Antarctic research, definitely for the moon. And I really continue to do research and stay involved in the Antarctic program, given that we're planning to go to the moon. And I think one of the reasons we won this competition is because we had the experience of the moon. So this is a concept for an Antarctic base to do exactly that, to do simulations of space for lunar and Mars exploration. How do we might take systems and assemble them in that environment, in that extreme environment with space, where it's really difficult to operate with gloves and very cold weather. It slows you down. There's a gateway vehicle being built right now. The idea would be in a lunar orbit, and it would serve the idea of going up and down on the moon and maybe around the planet, and that would be a transfer vehicle where both cargo and humans will get on land and the landers to go up and down to the surface of the moon. And eventually we'll be looking at long-term vehicles to go to Mars, where we will spend close to a year on the ship and transfer, and then we would have to be in almost a year in orbit or on the surface of the moon, but on Mars, I mean. So basically the really long durations, 2 to 3 year missions or to go to Mars, and that will become and then I think the moon will be the perfect place to learn how we do that and can we survive that and be sane and return everybody back safely. So anyway, my dream is in the future we will have really large number of people living in space, and we will have hotels on the moon and orbit for people to experience that, and also manufacturing facilities, manufacturing things that we cannot manufacture here, given the reduced gravity or the no gravity. We will be able to do alloys, crystals, and a bunch of other things that would be really beneficial to Earth. And as I always said, we're going to space for the Earth. The Earth, I never advocate the idea that we will go to Mars and escape the Earth. The Earth is the only spaceship that we have. As Bucky Fuller said, Bucky Fuller was an advisor to me, by the way, when I was doing my undergraduate thesis and my master's. We were in touch for several years. And so basically, it's all about this beautiful planet that we have, and learn about it through satellites and information that we're gathering from space. And how do we take care of this, and learn about technologies and way to live and be more sustainable, and all these things that we have to do in space, how we do it today. So sorry I went a little bit over time there, Sandra. So, but this is it. Thank you so much for listening.
Thank you so much, Guy. It was just in time. It was super interesting. Thank you. Let me share. Okay, right. This is very good. So we have a few questions, please. I would like to ask the students that would like to turn the camera on, please do it. Otherwise, it's okay if you keep it off. Many interesting projects. Congratulations, Guy. Okay, let's start with the questions.
It's a long life of being spaced out, so.
I have, if we have time, I have some questions as well concerning your sailing trip. Okay, the first question is by Karagosrim Durganbek. Please.
Hello, thank you for the very inspiring lecture. I was wondering, when you were mentioning the feedback that NASA was collecting from Skylab astronauts, I was curious which feedback from Skylab astronauts you could implement in your own work, and which parameters were most critical in your design.
Yeah, no, that's a tremendous amount. I suggest anybody that is interested in designing, anything in zero gravity should read those reports, as I mentioned, lessons learned from Skylab. They're available. To me, it was orientation was a major thing, because in the case of emergency, orientation is everything for safety. You need to understand where you're located, which way is up, and where to run to. I never forget being on the South Pole Station, and we had alarms for a fire, and immediately the local guys that live there, for the year, they knew exactly where to go, where to run, find the place they needed to be. And the same thing happens to zero gravity. You have to be able to do these things. And the Skylab astronauts got sometimes lost inside a module that didn't have a up and down. It was a circular module that was attached to the main space. The lighting was really around the perimeter. It was no up and down. All the walls were very similar, and they every time they went through that space, they had to spend a few seconds that could be critical in emergencies to orient themselves, and that's not a good thing. So that's how, we did studies on lighting and color and graphics. How do you read a label in zero gravity and so on? And what do you use in terms of space and floor reference where the astronauts are basically attached to the vehicle because they have the stirrups, or in Skylab they had these cleats. That was a major also lesson in restraint systems. The galley, for instance, on the Skylab was too low because we designed it almost to be sitting down. That was the way the design was, and it needed to be higher because the posture, we didn't understand the human posture and the ergonomics of zero gravity. So all those elements of ergonomics and how our body behaves without gravity were critical to design for every aspect of design, and we reviewed it many times, and also videos of that to really understand what this neutral buoyancy, we call it neutral buoyancy posture, which happens when you go in a swimming pool. If you wear a snorkel and a mask and you let your muscles relax, that is the neutral buoyancy of space. Your body will look that way. It's sort of a curve. We don't stand straight because we don't have the gravity. And on Earth, we have our bones that lock themselves up, so we don't have to hold ourselves with muscles. The bodies carry our load, the compression, and that doesn't happen in zero gravity. You're totally relaxed, so the muscles control our structural, our bones, and bone structure. So it's really it changes dramatically in zero gravity. So these are kind of major areas of being aware of how we as humans change because of that lack of gravity.
Great, thank you very much. It was a very interesting and elaborate answer. Thank you.
Thank you.
Thank you, Guy. I have a question. Have you ever had the chance of comparing these results with the results from the Russian side?
Well, I have been, in Russia and even in the Soviet Union during this time. Actually, in the 80s at SIXA, we would take our students to Russia. We would take our studio to Russia, to the Soviet Union then. We were in contact with, we actually ran competitions with the School of Architecture in Moscow, and some of the designs, and then we did the final critiques in Moscow. And sometimes we brought some of the Soviet students here to Houston, and so we were able to visit the laboratory for extreme environments, and I can't think of human problems. I can't think of the name right now, but run by this famous scientist. She's fantastic. Anyway, and so we did have some interaction, yes. And they used a lot more the research done in color than the US and the Europeans. They actually applied this idea of using earth colors, earth tones to the spacecrafts. And you can see that in Mir and Soyuz and so on, where we didn't.
Okay, great. Thank you. Mara?
Yeah, I do also have a question. It regards on what would you say can we learn from the space architecture here on Earth? So, for example, planning with much less space, for example, or social structures or cohabitation in confirmed environments. So, for example, we will be more people in the future and the space will not grow with us. So, and in the space, there's also few less space. So what could we learn from that?
You mean architectural space inside a building, or you're talking
No,
about
in
population
space,
of the Earth?
you're planning with very optimized structures and very thinkable of what could be where and specific and stuff. And what could we learn therefore for the architecture on Earth, for example, for living buildings or something?
Well, we certainly could make our buildings way more efficient. You know, it seems that we're going the different, even on the different direction, because buildings are much more massive these days in volume. We all like open atriums and very large spaces and so on Earth. And if you look at even the architecture of the 60s and 70s and 80s, it seems that buildings are getting more and more on steroids and, you know, becoming more, you know, they're larger and more extravagant, if you will, in terms of the amount of volume. But, you know, we're on Earth and it's not that costly. So, you know, I think we're building some really human-centered buildings more and more, and rather than the way they were before without light and you know, as much light in terms of windows and airy spaces and so on. So I think we're building a lot healthier buildings today than in the past, and certainly for the past 50, 100 years, with when we started inventing plastic and using toxic materials. So that is a key element of space, that we cannot take plastic to space. We cannot take toxic materials. They're very strict selection of materials like metals and glass and so on, because they cannot outgas, what we call outgassing. Outgassing means, you know, the toxic materials that come out of dyes that we put on fabrics or paints that are toxic and so on. That is not something that we want to take to a closed loop environment, you know, where you have to recycle all the air and so on and rebreathe it, and then you have to scrub those gases from that. So it's costly, it's dangerous, and so on. So I think and from that point of view, I think we are learning to maybe build healthier materials. And obviously, I think I'm an architect, you know, so I approach the design of anything in space as an architect of Earth. I really never really called, until lately people call themselves space architects. I really never called myself a space architect. As a matter of fact, I hid it from my clients, because they would say, well, you can never design my house if you design this kind of giant, you know, very mechanical systems. I don't want to live on that thing. So, you know, but so it's basically, from my point of view, I'm an architect here or there. It doesn't matter. Just give, you know, we look at the environment that we design for humans, based on the environment and the circumstances of the site. So I think that is a key element of going now to the moon and so on, is really to adapt to that. And then our contribution of architects is this idea of putting systems together that are pleasant to the human in terms of the volumes, the spaces, the light, they're healthy, a place that you can actually live and work in a mentally healthy and physically healthy environment. You know, and I think that's our role. Our role is to create spaces that are protecting us from the environment. And just like we do here, we don't want buildings leaking and, you know, having water coming through the roof or temperature and so on and so on. So to me, the rules are exactly the same. Our role is exactly the same. Even though the characteristics of the environment changes. As I always say to my students, we're human. We're human here, we're human on the moon, we're human in space. We still have this little brain that we carry with us, and our physical conditions of, you know, 10 fingers and legs and arms, and we move through the environment through that. In space, the space environment, particularly in zero gravity, is much more tactile, I call it, because we move with our hands. We grab things to propel ourselves. It's not like you can be in a building today without touching anything. You know, you have automatic doors, you walk through, you never touch The only thing you touch basically on Earth is the handle on the door or something like that. But we really do not touch our buildings very much, other than the furniture. So in space, you actually do. You know, you're really swimming through it. You're bouncing throughout the space or going up and so on. You have to stop yourself as you're flowing through it. So, so in that sense, then that tactility needs to be addressed in zero gravity, which is not so much here on Earth, is not needed.
Thank you.
Right.
Wonderful answer. Thank you, Guy. I have an addition to this because it fits to one other question. It's twofold. First of all, I mean, you explained what an architect does and therefore space architecture is, which I like very much. But why do you think space architecture is still considered so futuristic? Even if it's not, you know, we have been in space for many, many years, and especially with younger people, I would say it is considered very technical, futuristic, something that is for tomorrow or for another world. Why do you think is that?
Well, it is that way because it is futuristic, because there's very little built. We only have one laboratory. We had built another laboratory that disappeared, and this one is going to melt on the atmosphere and is going to disappear within the next decade. So it is a remote place, and it is very few people. I've been very lucky because I was born and raised and arrived in Houston at the right time at the right place. Not because I really wanted to do this, because it was luck, really, how I got involved in this thing. It's just I got there at the right time in the right place. And this is the right time and the right place for the future for every one of you, because we have much more access, like I said at the beginning of my talk, and many more countries and now companies are planning to go to these environments. So there will be way more work than it was when I started this business, right? So that's the exciting part. And it is exotic because truly it's like building in the middle of the Amazon jungle is exotic. Building on the Antarctic is exotic because these are very remote areas, and each one brings different conditions that we need to address as architects. And how do we use local materials, and how do we actually get the material there to these remote spaces? So it is difficult. It's not highly technical. I think it's common sense, and I think all the things that we learn, I think, in school in terms of planning and how to assemble a building, and how to distribute uses for the building, and the human-centered design of how do we bring people together, how do we give them privacy, and all these things apply. So, foundationally, I think it's the same problem. It's the same issue, but this idea of going to space and to this very exotic environment is still new and exciting. And I think that's why we find that there's so much interest today with students. And I don't think, like I said, I'm teaching at Arizona State University. We had 30 people in the studio this year, this past semester, which is too many. But it's not about turning every architect into a space architect, but it's a bit of like the first question of how do we learn things that we are doing or thinking about space, and how do we bring it to Earth, and vice versa. So it gives us as designers a different way of thinking. It opens up doors in our brain and these circuits in our brain to think in ways that could be very applicable to Earth. If not in the way that you bring a building together, but in the way you think about the design, the philosophical aspect of it. And I think this could be quite beneficial for the planet and for us humans.
Thank you, Guy. I think the question from Aim fits very well.
Hello, I have another question, and it's regarding these images of clutter you were showing of the workstation. and how much useful space is actually taken away. And I was wondering if there is a strategy or a concept being considered to deal with the loss of uh, useful space and spatial qualities in the workstation, such as maybe possible expansions or new working station module, or, for example, getting rid of all the unnecessary clutter. And is the clutter affecting astronauts performing tasks, research, or even simple flow of movement and rotation in working space? And I believe it does affect the astronauts and their performance, and therefore I'm wondering if you're considering to deal with it in an architectural way or any other. Thank you.
Yeah, that's a very good question because the place is a mess right now, the space station. But again, you're living in a very small space for 24 years without ever having an outdoor where you can throw they do get rid of things. They do produce garbage, and garbage gets put on modules that burn on our atmosphere and disappear, right? So they do get rid of a lot of clutter and things that they know we will not use, or they are not longer functional. But all the other things that could be functional, that are functional, but they don't use, and other things that are materials that they might use to repair other things, stay there. And I can tell you from sailing around the world, you don't throw anything away when you're in a remote area like that, because you cannot go to the shop or the hardware store and buy a wire or a new plier or a new tool or something. So you keep everything that you think you might use. And I think we all do that here on Earth as well, in our homes. Well, yeah, I don't know, but I might use this piece of, wire or fabric, and I won't throw it away because who knows when I need it. And usually when you throw it away is the day you need it. So that's human behavior. And I think, but also planning. I mean, you want to have things there because you don't want to have them shipped again. So they do keep a lot of things that they do not use. And as you are living in a remote area, there's so much storage. I mean, truly everything is full in the space station. All the storage is full, and there's no more modules coming out. So that's why this thing looks the way it does. And in terms of the clutter, I don't think the astronauts complain about the clutter. They complain that they can't find things, so they have to document where they left the scissors or this piece of equipment. So sometimes they call the ground and ask the astronauts that were there before, "Hey, where did you put this thing? Do you remember where you left this device?" So that conversation goes on all the time. But I feel, as I said, being an architect, and I want everything clean and not cluttered and very simple, white and very minimalist in many ways. That's the way the original design of the space station was. I feel that astronauts get totally bored when the space looks like that. This is a new thing that I've been thinking and researching. Is the idea that if we are going to spend a lot of time in a very small environment, actually clutter and complexity adds to the experience of living in it. It's sort of like having a photograph, on your wall of an object or a design of a photograph that is realistic, and then you study it and you look at it, and once you studied it enough, you really understand that. But if that photograph of that piece of artwork is abstract and complex, you can look at it and you can turn it over in different ways. You can upside down, you can turn it sideways, you can illuminate it different ways, and it will change all the time. And I really experiment with abstract art in that way. And abstract, basically living inside a space station is living inside an abstract sculpture that is in constant motion, that it has a dynamic. So it's never the same. So when you go into this space, it's sort of interesting because it creates something else, or in terms of shadowing and where things are located and so on. So, this came to me in India when I was looking at this very complex building with little extraordinary amount of sculpting pieces and objects and sculpting and figures and so on. And I'm looking at this thing, I said, I can look at this wall for 10 years and I will never understand it. And this is where it all came about living in isolation and having an environment that actually helps the brain develop new ideas of your perception rather than a white wall with a blue line, a Mondrian painting, which it could be quite interesting and lovely and so on. But 10 years, 20 years looking at the same painting? Anyway, I'm not sure I answered the question.
Yeah, but this is very, very interesting point of view. I've never have thought about that, because I immediately started thinking about if they're having troubles finding things, maybe an organizational system might be a good solution to that. But then you come with this point of view that people in confined spaces like that, in isolation, that don't have this distance that we have and this complexity of the world that we have, that this clutter creates this complexity for them and makes it curious and interesting. That's a very interesting point of view. Thank
As a matter
you.
of fact, the storage system, it does work. I mean, it is all labeled and we're supposed to register. I mean, it is designed. It is there.
Mhm.
And it really works. I mean, people do find stuff, but some things get lost.
Yeah.
So it's a big problem when you have a bunch of people living together and everybody leaves things, even though they're quite trained and disciplined, but still, things do get lost.
Yeah. Like everywhere. Yeah. Thank you.
Thank you for this beautiful question. And Guy, this would be an interesting start of a conversation on complexity versus chaotic.
I would love to have
geometries, because we have, together with the psychologist Charles Bishop, we have worked on this issue. What you mentioned, that trees are very complex.
Yes.
But it's soothing for the eye.
Yeah.
Whereas the pictures from the space station with all these cows, it's not really soothing. It's and there is a difference between the geometry that it's based. So it would be interesting to continue this discussion.
This is I could say maybe controversial, but I do. The deeper I go, the more I tend to complexity is better than minimalist and simplicity.
Oh yes, well, chaos is not. There's a difference, right, between complexity and chaos, because there is some order in complexity. Well,
chaos is not that bad either. For
yeah.
our brain. But anyway, that's a long. We could do a little symposium on it.
That would be very interesting.
It would be.
And we have with some architectural solutions.
Yeah, well, I have a whole lecture about it.
Let's have maybe one space for one last question. Is there one question? Otherwise, or Mara, do you have a question because your camera is on? No. Okay. I found it very beautiful that you have always worked with 1 foot in space and 1 foot in space on Earth, right? So in a way, and at the beginning you said that travel in your sailboat changed you, and we could talk hours about it. Can you maybe, as a roundup, say also what you're teaching? What we can learn from living, working, thinking about those extreme environments, and why we possibly need it for our life on Earth?
Oh, absolutely. I think space is the perfect example of collaboration, first of all, where you learn to live together with different people, with different backgrounds that are able to accomplish complex missions. So I think there's a tremendous amount to learn about that. About how do we work together here on Earth, and learn from how astronauts work together to solve some difficult and complex problems. So that's number one. And then the other one is, what is it? How much do we need to live? How much stuff do we need to live? How much, how do we actually manage waste? How we manage our environment? How do we control and measure ourselves and with respect to the environment that we live in, and not abuse it, and not, so there's just a tremendous amount of things that I think we would learn on the moon as we have learned on the Antarctic, but actually the Antarctic experience have not filtered into society because it's not as exposed as space. We don't talk about every day on the Antarctic. You don't see it in the news, but you see every day something going on in the space station or launches and so on. So I think space would be a great place for us to understand what I talk about: recycling buildings, reuse the materials that we take. I mean, to me, on the moon, every piece of metal is basically a gold mine, because you can melt it, you can transform it, you can build new elements with that, new things with it. So that whole idea of the circular economy really applies, and circular design applies for space, and more and more we will see it when we're able to 3D print our tools, our parts, and so on from metals and materials that we took to the moon or space or Mars. So to me, those are basic things that I think will happen whether we like it or not. We will learn from it.
Thank you, Guy. I would love to continue, but our time is limited, and thank you very much for sharing your ideas and telling our students about your project. I would also like to thank you for your fresh view too. A lot of things I heard before from other people, but a little bit different from you. So it was really interesting. Thanks a lot.
All right. Well, thank you so much for the invitation. A pleasure seeing you always, Sandra, and meeting your students. So I wish you all a happy holiday, a fantastic new year full of adventure and exploration. So good luck and good research to you all.
Thank you. Bye-bye.
Bye-bye.
Thank you.